Welcome to our channel. Let's start our new video. Today is our topic is deep learning. Deep learning is a subfield of artificial intelligence and machine learning that focuses on creating algorithms and models inspired by structure and function of human brains neural networks. It is particularly effective and at handling complex tasks such as image and speech recognition, natural language processing, and even playing games like chess and Go at a superhuman level. At the heart of deep learning are artificial neural networks, which consist of layers of interconnected nodes, neurons, that process and transform data. These networks can have multiple hidden layers, allowing them to capture intricate patterns and relationships in the data. Deep learning has become immensely popular due to its ability to automatically learn and extract features from raw data, eliminating the need for explicit feature engineering. Some key concepts and technologies within deep learning include: number 1, convolutional neural network. CNNs are particularly well suited for image and video analysis. They use convolutional layers to automatically learn special hierarchies of features within images, enabling tasks like object detection and image classification. Number 2, recurrent neural network (RNNs) are designed to work with sequence of data such as time series data or natural language. They maintain an internal memory that allows them to capture information from previous steps in the sequence. Number 3, long short-term memory networks. LSTMs are a type of RNN designed to mitigate the vanishing gradient problem, allowing them to capture long-range dependencies in sequence more effectively. Number 4, gated recurrent units (GRUs). Similar to LSTMs, GRUs are designed to tackle the vanishing gradient problem while being computationally less complex. Number 5, transformers. Transformers have gained significant attention in natural language processing tasks. They use a self-attention mechanism to process input data in parallel, making them high efficient for tasks like language translation, text generation, and sentiment analysis. Number 6, generative adversarial network. GANs consist of two neural networks, a generator and a discriminator, that are trained together in competitive manner. GANs are used for generating realistic data such as image, music, and text. Number 7, transfer learning. This technique involves training a deep learning model on one task and then using the pre-trained model's knowledge to aid in training on different but related tasks. This is especially useful when dealing with limited amount of data. Number 8, autoencoders. Autoencoders are neural networks used for unsupervised learning. They aim to reconstruct input data from a reduced dimensional representation, which can be useful for tasks like data compression and Feature extraction. Number 9. Deep reinforcemental learning. This combines deep learning with reinforcement learning, enabling AI agents to learn how to take actions in an environment to maximize cumulative rewards. Deep reinforcement learning has achieved remarkable success in tasks like playing video games and robotic control. Number 10. Neural architecture search. NAS is the process of using machine learning algorithms to automatically discover the optimal neural network architecture for given task, reducing the need for manual architecture design. Deep learning offers numerous advantages that have contributed to its widespread adoption and success across various fields. Some of key advantages include: number 1, feature learning. Deep learning models automatically learn relevant features from raw data, eliminating the need for manual feature engineering. This capability allows them to capture complex patterns and relationships that may not be obvious to human designers. Number 2, hierarchical representation. Deep neural networks are capable of learning hierarchical representation of data. This means they can understand both low-level features and high-level abstractions, enabling them to handle tasks that involve multiple levels of abstractions. Number 3, flexibility and adaptability. Deep learning models can be applied to a wide range of tasks, from image and speech recognition to language translation and playing games. Their versatility makes them suitable for various applications without requiring major architectural changes. Number 4, state of the art performance. Deep learning has consistently achieved state of the art performance in many challenging tasks. For example, convolutional neural networks have revolutionized image recognition, and transformers have greatly improved natural language processing tasks. Number 5, reduced feature engineering. Traditional machine learning often requires domain expertise and substantial effort in designing relevant features. Deep learning reduces the reliance on expert-crafted features as it learns features directly from data, making the development process more streamlined. Number 6, transfer learning. Pre-trained deep learning models can be fine-tuned for specific tasks with limited data. This enables faster development cycles and better performance in the scenarios where acquiring large amount of task-specific data is challenging. Number 7, scalability. Deep learning models can scale to handle large datasets and complex tasks. Advanced in hardware such as graphics processing unit and specialized hardware like tensor processing unit have enabled efficient training of deep networks. Despite these advantages, it's important to note that deep learning also has limitations, including the need for substantial computational resources, large amount of data for effective training, and challenges in understanding and explaining the decisions made by complex models. It's crucial to carefully consider these factors when applying deep learning to specific tasks. Thank you for watching our video.